Training to all of you. I'm audible?
Yes, you are audible. Yeah.
Okay. So first of all, I'm thankful to the Rajesh for inviting me to give a lecture in this seminar. Thank you very much. Today I'm going to talk on energy of graph. The energy of a graph is nothing but the sum of the absolute values of the eigenvalues of the adjacency matrix. Okay. So we'll consider the finite graph, which is simple undirected with n points and n number of lines. So vertex set is denoted by v of g equal to v1, v2, vn, and h set vg is v1, v2, vn. Okay. Then the adjacency matrix of the graph G is nothing but the square matrix of order n, whose ijth entry aij is 1 with the vertex vi is adjacent to the vertex vj, and it is to the 1 minute. Index with the vertex set, and its ijth entry is 1 if the vertex vi is adjacent to the vertex vj, otherwise it is 0. So characteristic polynomial graph G is nothing but the characteristic polynomial of its adjacency matrix, that is the determinant of lambda minus a of G, where I is the identity matrix of order n. And the eigenvalues of the adjacency matrix are the eigenvalues of the graph, and their collection is called the spectrum of G. So if you take denote the lambda 1, lambda 2, lambda 2, the distinct eigenvalues with the respective multiplicities m1, m2, mk, then the spectrum of a graph is written in this form, that is lambda 1 appears m1 times, lambda 2 appears m2 times, like that lambda k appears mk times. So this m1 plus m2 plus and so on mk is nothing but total number of points here. Okay, the sum of mi is here. Okay, so these are the distinct eigenvalues appearing m1 times, m2 times, and so on respectively. So main topic of this talk is energy of a graph. Okay, so we'll give more stress on this energy of a graph, and I'll outline today's talk. I'll use some bounds for the energy of a graph, as well as the and we'll do the we'll discuss about the hyperthermal. Energy of a graph, as I told, so in mathematics, this quantity was put forward by the Iran Gutmann, who is a Finnish from the Serbia in the year 1978. But its root goes back in the 1930s. Okay, that time also this concept is used, but not that much popular at that time. But Gutmann found its mathematical importance. Okay, this quantity. So for example, consider this graph on 6 points, v1, v2, v3, v4. Okay, so its characteristic polynomial is lambda raised to 6 minus 9 lambda raised to 4 minus 4 lambda 2 plus 12 lambda square, and its roots are 3, 1, 0, minus 2 with respect to multiples 1, 1, 2, 2, 2 and minus 1. So 3 is 1 times, 1 is 1 time, 0 is 2 times, and another eigenvalue or root of this equation minus 2 is 2 times. So to add the sum of the absolute values of these eigenvalues, it is 8. Okay. So energy of this graph is 8. Okay, for this. So we know the spectrum of the complete graph Kn as n minus 1, and the remaining eigenvalues are minus 1. Okay, this is the characteristic polynomial complete graph. Okay, graph where every pair is adjacent. So spectrum of Kn is this. So from here, we can write the energy of a complete graph as 2 times n minus 1. Okay, 2 times n minus 1. And for the complete bipartite graph, the eigenvalues of root pq, another is minus root pk, and the remaining are 0, that is p plus q minus 2 times. Okay, so this complete bipartite graph pq has exactly two non-zero eigenvalues. One is root pk, another is minus root pk, and remaining 0. So energy of complete bipartite turns to the 2 times the root of pq. Okay. Similarly for the cycle Cn and Pn. Okay, because we know the spectrum of this, so one can easily write the energy. Okay, for the cycle Cn on n points, the energy of Cn is 4 times cot pi by n. If n is congruent to 0 mod 4, if n is congruent to 2 mod 4, then it is 4 cosec pi by n. And if n congruent to 1 mod 2, then it is 2 times cosec pi by n. Similarly for the path Pn, the energy is 2 cosec pi by 2 into n plus 1 minus 2 if n is congruent 0 mod 2, and for n congruent 1 mod 2, it is 2 cot pi by 2n plus 1 minus 2. Okay, this is because it is we know the spectrum of the cycle as well as the Tn. Similarly for the complete graph as well as for the complete bipartite. Okay, so one can put in this form the energy of these graphs. Okay, but one of the remarkable chemical application of this spectrography is based on the close correspondence between the graph eigenvalues and the molecular orbital energy levels of pi electrons in conjugated hydrocarbons. Okay, not in the whole. So see a little bit about the Haeckel molecular theory. In 1930, the German scholar Erich Haeckel made certain simplification of Schrödinger wave equation. What is one? The wave equation, wave function psi are the solution of Schrödinger wave equation, that is h minus e equal to 0, where h is the energy operator and e is the electron level. So this Schrödinger wave function Haeckel replaced with the secular equation as determinant of h minus es. Okay, so we have taken determinant of this and instead of this es and es. Okay. So where h is alpha I plus beta I and s is I plus sigma I. Of course, alpha, beta, and sigma are constants. No? I is the identity matrix, whereas A is the adjacency matrix. So you put alpha is 0 and beta is 1. This h is nothing but the adjacency matrix. H becomes the adjacency matrix, and for sigma 0, s becomes the I. So it will be determinant of A minus lambda equal to 0, where A is the adjacency matrix of the molecular graph. Okay, I will tell what is meant by molecular graph. So as I told you here, if alpha 0 and beta 1, then S becomes the adjacency matrix. Okay. So spectrographs can be used to calculate the energy levels of conjugated hydrocarbons as calculate the Haeckel molecular orbital method. Okay. With respect to this method, only one can find the means we can correlate the spectra as well as the energy levels of the molecule. Okay, so I will tell this is a molecule that is butadiene C4H6. So molecular graph is for a carbon atom, we take the vertex corresponding to carbon of the vertex, and hydrogen atoms are ignored. Okay, hydrogen atoms are ignored. Okay, because it is not contributing much into this. And the two what I said adjacent, if there is a carbon bond, that is a bond between the two carbon atoms, then we will put the line. Okay, so for this molecular graph, this molecule, the molecular graph is this people. Okay, and the matrix H. Okay, so here index with the vertex set. Okay, and if there is a line between 2 points, it put beta, otherwise 0, and diagonally it is alpha. Okay, diagonal entries are alpha. If there is an edge between 2 points, then it is beta, otherwise 0. So it is turns to the alpha I plus beta I. Okay, so if you take alpha 0 and beta is 1, then it becomes the simply adjacency matrix of a graph, this molecular graph. So H is alpha I plus beta I. So suppose eigenvalues of H are taken as a epsilon I. Okay, and the eigenvalues of the adjacency matrix are say lambda 1, lambda 2, lambda n, and of course the eigenvalues of the identity matrix are 1, 1, 1. Okay, so the EI will be in terms of alpha plus beta lambda. Correct. So from this above equation, okay, if these energy levels of the epsilon I of the pi levels, they are related with the eigenvalues with this relation. Epsilon I is alpha plus beta lambda. Okay, because H is expressed in the form of alpha plus beta A. Okay, so in the HMO method, the total pi electron energy is nothing but sum of Gi into this epsilon I, where Gi is the occupation number. Okay, that is number of electrons, total number of electrons in that particular orbit. Okay, so total pi electron energy will be sum of Gi into epsilon I. Okay, and this Gi is the occupation number as I told. Okay, then replace this epsilon I with this alpha plus beta lambda I. So what it will get summation of Gi into alpha plus beta into summation of Gi into lambda. Okay, and sum of Gi is n, so it is n alpha. Okay, it is n alpha. Just simply replacing this here in this. So you get total pi electron energy of the molecule is n alpha plus beta into summation of Gi lambda. Okay. But in the most of the cases, if lambda is positive, then this Gi is 1. Okay, sorry, Gi is 2, and if lambda is negative, then this Gi is 0. In the most of the molecule. Okay, so for majority of conjugated hydrocarbon, Gi is 2 if lambda is positive, and is 0 if lambda is less than 0. Okay, therefore from here, okay, from here for lambda it is lambda for positive lambda it is 2, and Gi is 2, and for negative lambda it is 0. So if this becomes n alpha plus 2 times summation of 2 times lambda I over the positive eigenvalues. Over the positive. So total pi electron energy will be n alpha plus 2 beta sum of lambda I over positive eigenvalues. And since the diagonal elements of the adjacency matrix are 0, so trace of a matrix is 0, it means that sum of the eigenvalues is 0. Okay, that is sum of the positive eigenvalue is same as the sum of the negative value, only they differ in the sign. So combining all those eigenvalues, one can write instead of writing 2 times sum of lambda I over the positive, we can write summation of mod of lambda taking I from 1 to n. Okay, means considering all the eigenvalues, positive, negative as well as 0 also. Okay, the 0 is not nothing very complicated, right? Because 0 for 0. Okay, so total pi electron energy can be n alpha plus beta into sum of mod of lambda I. So n is fixed here, number of electrons, alpha and beta are constant. So this quantity, only this, that is the summation of mod of lambda I, is taken as a graph energy. Okay, is taken as a graph energy because this quantity n alpha as well as beta constants. Okay, so graph theory we are interested only in this summation of mod of lambda I. So thus the graph energy, the Goodman put forward in this form, summation of mod of lambda I. Okay, then lambda I are the eigenvalues of a adjacency matrix of a graph in general. Okay, in general, if lambda 1, lambda 2, lambda n are the eigenvalues of any graph G of order n, then the energy of that graph is defined as summation of mod of lambda I over all eigenvalues. So this definition he put forward in the year 1978. Okay, so till 1999, there were only 1 or 2 papers there, but afterwards, from 2000 onwards, many people are working on the concept, and several papers have come out on the graph energy. Okay. This quadrant integral formula we put in the 1940. Okay, that is energy of G can be expressed in the form of integration. That is 1 by pi integration from minus into plus infinity n minus I lambda pi dash g I lambda divided by pi j I lambda data. So this bold I is square root of minus 1, and the pi dash is the first derivative of the characteristic polynomial. Okay, I will briefly outline the proof of this result. Okay, suppose pi g lambda is the polynomial of degree n in the complex variable set z, and lambda 1, lambda 2, lambda n are its roots. Okay, then pi g lambda can be written as, that is pi g z as product of z minus lambda j. Okay, because lambda 1, lambda 2 are the roots. So differentiating this with respect to z and then dividing by all with the polynomial pi g z, one can get this pi dash divided by pi as summation of 1 divided by z minus lambda j. Okay, so differentiate and divide by the polynomial. Okay, then multiply both side by z. We will get here z pi dash divided by pi as summation of z lambda minus lambda j. Then just simplifying, that is dividing these terms, we will get 1 plus lambda j, z plus lambda j, or just putting this one outside, so you get sum of 1 is n, so n plus summation of lambda j divided by z minus lambda j. Then take n on the other side, so the z pi dash divided by pi minus n is summation of lambda j divided by z minus lambda j. So as the mod z tends to infinity, okay, this mod z tends to infinity, so this quantity tends to 0. Okay, so z pi dash divided by pi minus n tends to 0 as mod z tends to infinity. Okay. Then consider this contour, okay, with positive oriented, okay, as shown here. Okay, so these are the positive eigenvalues, these are the negative eigenvalues. Okay, so we'll integrate over this contour now. So according to the Cauchy's formula, 1 by 2 pi, it is well known, we know that 1 by 2 pi integration of dz divided z minus z naught is 1 if z naught is in the interior of contour, and it is 0 if z naught is the exterior of the contour. Of course, z naught is in the interior as well as on the boundary. Okay? So dz divided by z minus z naught is 1 if it is inside, otherwise 0. So we'll use this now. So consider this 1 by 2 pi integration of z pi dash divided by pi minus n, that is 1 by 2 pi integration of, okay, z pi dash divided by pi minus n is this one, summation of lambda j divided by z minus lambda j. Okay, so that is here. Okay, then just interchanging integration and summation, it is sum of j from 1 to n lambda j divided by 2 pi integration dz divided z minus lambda j. So For this, we use this Cauchy's formula. Okay. It is 1 if Z0 is in the interior, otherwise it is 0. So this becomes 1. Okay. This becomes 1 for the inside. Inside means only for the positive original. So it is 2 pi into 1. So that gives summation of lambda j over the positive original. And summation of lambda j over the positive original is nothing but half of times energy of g. Correct. So energy of G will be these two cancelling. Energy of G will be 1 by pi I integration this term. Okay. So in the limiting case, when this gamma plus becomes infinitely large, okay, the only non-vanishes condition to the above integral comes from the integration along the y-axis. Okay, because as Yan change with that term changes 0. Right. So this integration, okay, this integration will be split into the two parts as from minus into plus infinity and then infinity to minus infinity. Okay. So from minus into plus infinity, that is along the this curve. Okay, as n tends to infinity, this is tending towards 0, so it vanishes. It vanishes. So only left along the y-axis. Along the y-axis from plus infinity to minus infinity. So this term vanishes left here. Okay, along the y-axis, z the x plus I y, so x is 0. So instead of z, we will write here I y. Okay, I y. So just simplifying, one can get here 1 by pi into some minus into plus infinity n minus I y pi dash divided by pi in terms of I y. I replace y with lambda. So energy of G can be expressed in the form of integration like this. 1 by pi minus infinity n minus I lambda pi dash gi lambda divided by pi gi lambda d lambda, where this small I is nothing but square root of minus 1. Okay. Then this is the first one obtained by Maclaurin in the year 1978. So for any graph G with n points in m s, the energy of G lies between square root of 2m plus n minus 1 determinant of a to the power 2 by n and square root of 2m. Okay. The proof is simple. We know that the geometric mean of positive numbers is not greater than their arithmetic means. Okay, so using that type, summation of mod of lambda into lambda j upon n into n minus 1. Okay, this is arithmetic mean of these terms. Okay, product of the lambda eigenvalues of 2 at a time. Correct, is more than the geometric mean, that is pi of or product of lambda and lambda j to the power 1 by n into n minus 1. So this is nothing but product of lambda to the power 2 into n minus 1. So that turns to the product of lambda to the power 2 by n and product of the eigenvalues, okay, with absolute, okay, absolute eigenvalue. It is nothing but absolute of determinant of a to the power 2 by n. Okay. So this summation of mod lambda into lambda j is greater than or equal to n into n minus 1 determinant of a to the power 2 by n. Okay, absolute value of determinant of a to the power 2 by n. Okay, so energy of G is sum of the absolute values of the eigenvalues. So squaring that, you get sum of lambda square plus sum of lambda into lambda j. I is not equal to j. And sum of lambda square is 2 times the number of lines. Okay, 2 times the number of lines. So that comes from the properties of the eigenvalues of a graph. Okay. And this second sum is more than n into n minus 1 determinant of a to the power 2 by. Okay, so that. So taking square root, we will get the lower bound as energy of G more than equal to square root 2m plus n minus 1 determinant of the power 2 by. Okay. And for the upper bound, we'll use the Cauchy score inequality. So for n tuples a1, a2, an and b1, b2 is bn, we know that summation of ai b whole square is less than sum of ai square, sum of bi square. So just simply replace ai with 1 and bi with mod lambda. So this will be summation of mod lambda square, and this is 1, 1, 1, so it is m, sum of lambda square. So again, I told sum of lambda square is 2 times m, and sum of mod of lambda square is also 2m. Okay, so energy of G will be less than equal to square root 2m. And equality holds for the graph K2 appears n by 2 times. Okay, that is matching. Okay, n by 2 times, and then equality holds. So these are the starting bounds given by the Maclaurin. One is lower bound and the another is upper bound. Then several bounds are expressed in the form of m, n, and other. Okay. The another one is given by Goodman, okay, in the form of the number of lines. Okay, so energy of G lies between 2 times square root m and 2m. Okay, so again put is from here. Energy of G square can be the sum of lambda square plus 2 sum lambda lambda j. And this quantity, this second sum, can be written as greater than or equal to 2 times mod of sum of lambda lambda j. Correct? This mod can be taken outside the summation. So sum of lambda square is 2m, and product of the eigenvalues, okay, product of the eigenvalues 2 at a time is the second coefficient. That is a2 divided by this one upon a naught. Okay, so from that one can get here minus m. Okay, minus m. So it is 4m. So energy of G is more than equal to 2 root m. And to get the upper bound, for all graphs n is less than equal to 2m. So energy of G is less than equal to 2mn, square root 2mn, that is given by Maclaurin. Okay, then n is less than 10. So putting that, you get energy of G is less than equal to 2. So this bound of energy is in terms of the number of edges. After that, Pullen and Moulton, they are given the bound for a graph in terms of number of points as well as number of lines. Okay, with condition that 2m is more than equal to n. So consider graph G with n points and n lines, and 2m is more than equal to n. Then only the energy of G is less than 2m by n plus square root of n minus 1 into 2m minus 2m by n whole square. Okay, so for this, what they have done, again taking the Cauchy square inequality and replacing ai with 1 and bi with mod lambda I. Okay, but I you have to start from 2 to n, not from 1 to n, 2 to n. Okay, so this becomes sum of mod lambda square I is 2 to n. Here one we are putting 1 on how many times? N minus 1 times. So this will be n minus 1 and this sum of lambda square. So this left hand side turns to the energy of G minus lambda 1. Correct? Energy of G minus lambda 1 whole square. And sum of lambda square is 2m. So I ranging from 1 to n. So this sum of lambda square from 2 to n can be written as 2m minus lambda 1 square. And then simplifying, that is taking square root and transferring lambda on this side, we will get energy of G is less than equal to lambda 1 plus square root of n minus 1 2m minus lambda 1 square. Okay, we will consider lambda 1 is the largest eigenvalue. Lambda 1 is the largest eigenvalue among all n eigenvalues. Then they replace this lambda 1 with a variable x. Okay, so this will be taken as x plus square root n minus 1 2m minus x square. So this is denoted by f of x, and this is a decreasing function. Okay, in the interval 2m by n square root 2m or x, and it is maximum when x is 2m by n. Okay, and lambda 1 equal to more than equal to 2m by n. Okay, the largest eigenvalue is always more than 2m by n. So f of lambda 1 is less than equal to f of 2m by n. Okay, so this is this right hand side is f of lambda 1. So energy of G is less than equal to f of lambda 1, that is less than equal to f of 2m by n. So replace lambda 1 by 2m by n. So we will get energy of G is less than equal to 2m by n plus square root of n minus 1 into 2m minus 2m by n whole square. Okay. Further, what they have done, they replace this m with x. Okay, replace m with x and then obtain again the bound in terms of n. Okay, this bound equality holds if and only G is n by 2k2 or G is kn or G is a strongly regular graph with two non-trivial eigenvalues both having absolute values equal to this. Okay, strongly regular graph means it is a graph which is a regular of degree r but not complete. Okay, with n points and every with parameters say n r a b. Okay, so n is a order of a graph, r is a regularity of graph. Every adjacent pair has a common neighbors and every non-adjacent pair has b common neighbors. So such graphs are called strongly regular graphs. Okay, so equality holds for the strongly regular with two non-trivial eigenvalues because every strongly regular graph has exactly three distinct eigenvalues. One is regularity r and the another two eigenvalues say lambda 1 and lambda 2. So those lambda 1 lambda 2 have the absolute values equal to this. And for that graph, the equality of this bound holds. as I told, further they replace this m with x, and again using the maxima minima, they obtain this bound. Okay, this is n into square root of root n plus 1 by 2 in terms of n only. Okay, in terms of order of a graph. Okay, and this equality holds if and only if G is a strongly regular graph with the parameters this. That is, n is a regularity. N is a number of order. N is the number of points of a graph. N plus root n by 2 is the regularity of graph. Then n plus 2 root n by 4 is the number of points where the every adjacent pair adjacent, and the non-adjacent pairs have n plus 2 root n by 4 common neighbors. Okay, and adjacent pair has n plus 2 root n by 4 common neighbors. Okay, but this equality holds for this particular graph, and that is for n equal to 64, 256, and so on. Okay, for other graphs, means for other order we don't know. Okay, for other order we don't know. Only for this means for this values of n, such graphs exist where the energy of G is equal to this quantity n into root n plus 1 by 2. Okay, then some more bounds. Just I will outline here. So is given in 214, that is if G is a graph with n points, n lines, and vertex degree sequence is d1, d2, dn, then energy of G is less than to this quantity, that is the square root 1 by n sum of di square plus square root n minus 1 2m minus 1 by n sum of di square in terms of degree sequence. Equality holds of course for n by 2 k2 or kn or strongly regular graph with two non-trivial eigenvalues with absolute value this, or it is n value. Okay, this is myself and so given again in the 218 another bound for the energy for a bipartite graph. Okay, so G is a bipartite graph with n points more than 2 m lines, and first Zagreb index, that is m1. Okay, so this is a Zagreb index. Sum of di square is called first Zagreb index. Okay, sum of the squares of the degrees of the all vertices is called the Zagreb index. That is first Zagreb index. Okay, and the partition is n1 n2 with condition n1 less than equal to n2. Plus another condition is m is less than equal to nm by n1. Then energy of G is less than 2 times square root m by n1 plus 2 square root n1 minus 1 into m minus m by n1. And equality holds if and only G is n1 k1s union this. Okay, k1 appears n minus n1 minus s n1 times. On this graph, the equality holds. This is another with another condition, that is n1 is less than n2, m is greater than n2, then energy of G is less than equal to pm by square root n1 plus n2 plus 2 square root n1 minus 1 into m minus m square divided by n1 n2. Okay, this is for the bipartite graphs. Right. Then about what about tree? So among all trees, okay, among the star Sn has minimum energy, whereas the path Pn has the maximum energy. Okay, you take all trees with n points. Among that, the star has minimum energy and the path has the maximum energy, and they are the unique graphs. Okay, they are the unique graphs. Then here gives the sequence. Suppose T1 is a tree obtained by joining the vertex to a terminal vertex of a star Sn minus 1. Okay. T2 is another tree obtained from the joining by two vertices to a terminal vertex of Sn minus 2. Okay. T3 is a tree obtained by joining a vertex of path P2 to a terminal vertex of a star Sn minus 2. And T4 is a tree obtained by joining a middle vertex of a path P5 to the terminal vertex of a path Pn minus 5. So here see in the figure. This is a star S9, the star graph with 9 points. This is T1n, means one point is joined to the one of the terminal point of a star of order 8. Okay. Here, this is T1n, this is T2. T2 is a tree obtained by joining two points to the one of the terminal point of Sn minus 2. Okay, so here it is joined to the S7. Here, the path T2 is joined to the terminal point of a star. And here, the middle point of a path P5. This is a path P5. Okay, its middle point joined to the terminal point of a path Pn minus 5. Okay, so this is with 9 points. These structures are shown here. Then if you calculate the energies among this, then the energy of this star, okay, is strictly less than energy of this T1, less than energy of T2, less than energy of T3, less than energy of any other tree, less than energy of this T4, and then it is less than energy of PL. Okay, CL. It is any tree on N vertices, different from star T1, T2, T3, T4, and Tn. Then energy of star is strictly less than energy of T1, less than energy of T2, less than energy of T3, less than energy of any other tree, other than this, less than energy of T4, less than energy of Tn. Okay, strictly it is. Okay, strictly. So here in the tree, if the coefficients of the polynomial, okay, coefficients of the characteristic polynomial, they are giving the relation of the this decreasing. For example, if you take first one of the tree, say coefficients are A1, A2, A, and another tree has the coefficients say B1, B2, and so on. If A1 is less than B1, A2 is less than B2, A3 is less than B3, and so on like that, then energy of the first tree is always less than energy of the second tree. Okay, second tree. So from that one can check this relation. Okay. Similarly here, to take this another two trees, ANK and BNK. Okay, so ANK is this double star. Okay, this side K points, and these are N minus K minus 2 points. Total it is N points. Similarly, this another tree, here K points, and here minus K minus. Then see, if you go on increase the value of K. Okay, if you take first 1 point here, then take 2 points, and then 3 points up to N by 2 minus 1. So energy of trees are going on decreasing. Okay. That is energy of N1 is less than energy of N2, less than and so on, up to energy of N by 2 minus 1. Similarly for this tree, BNK. First take 1 point, find the energy, then put here 2 points, 3 points, and so on. So energy is decreasing. And it will attain at N minus 3 by 2. The value of K will be N minus 3 by 2. That time it will maximum. Okay. Now already we have seen the Coulomb motor mode is this, and if G is a regular graph, then the 2m by n is r. Okay, so energy of G will be less than r plus square root r n minus 1 n minus. So simply replace 2m by n with r. So you get the energy of a bound for the energy of a regular graph, and this is equal for the complete graph. So consider this right hand side as a P2. Okay, that quantity P2. Okay, so in Balakrishnan in 2004. Showed that for every epsilon more than 0, there exists infinitely many irregular graphs such that energy of G is less, divided by B2 is always less than epsilon. Means this bound is far away from the actual value of the energy. Right. So there are the graphs. There are the graphs where the ratio is very, very small. And he posed the following questions for a given positive integer n, whether there exists an irregular graph of order n such that energy of G is divided by B2 is more than 1 minus epsilon, or some are less than n minus. Okay, means whether there are exist graphs or not, such that the energy of G is always near to this. Okay, far from this, it is there, but near to this, whether it is there. And the answer is yes. Okay, graph is there. And that is our group in 2008 as well as the BDC in 2010. Okay, we have given the graph, which is called the Paley graph. Okay, so Paley graph is a strongly regular graph with these parameters: n minus 1 by 2, n minus 5 by 4, and n minus 1 by 4. Okay, its spectrum is given here. Okay, spectrum is given here. It's a regular graph of degree n minus 1 by 2. Okay, and its energy is n minus 1 into square root n plus 1 by 2. And if you put the value of r into that quantity B2, it is turning to the n minus 1 into 1 plus root n plus 1 by 2. If you take the ratio of these two, energy as well as this B2 for this Paley graph, it is tending towards 1 as n tends to infinity. So this shows that there exists a graph. Okay, namely it is Paley graph. Okay, namely it is Paley graph, such that energy of G divided by B2 is more than 1 minus epsilon. Okay, but not for all n. Okay, because only for this n minus 1 by 2, these are the integers. Okay, your n should be like this. All these quantities are integers: n minus 1 by 2, n minus 5 by 4, n minus 1 by 4. From table you can see as the n increases, the ratio tending towards 1. Tending towards 1. Okay, so for large n, you can find the graph, namely this Pele graph, for which the affirmative answer of for the question of the bio question is there. Okay. But not for all n, as I told. Okay, so till it is open for whether for all n such graphs exist or not. Now come to the hypernetic graphs. So Maclaurin bound is energy of G less than equal to square root of 2mn, as we have seen. Okay, and for in the chemistry, for the molecular graphs, it is turning towards approximately a into square root of 2mn, where a is a 0.9. Right. So energy of G is almost equal to a into square root of 2mn. So among all graphs with n points, the complete graph has the maximum number of lines. Okay. So this quantity is maximum when m is maximum. Okay, for a fixed m. Okay, for a fixed m. This is more when m is more. Okay. So and m is maximum only in the complete graph Kn with n minus 1 by 2. So with that observation, Woodman concluded that among all graphs with n points, the complete graph has the maximum energy. It means that for any graph G with n points, energy of G is less than equal to energy of a complete graph, and energy of a complete graph is 2 times n minus 1. But this is not true. There are the graphs where this conjecture fails. For example, consider this graph, okay, on 12 points, and its spectra is the eigenvalue, that's eigenvalue 5 1 times, 2.2361 3 times, minus 2.2361 3 times, and minus 1 5 times. And its energy is approximately 23.416, whereas the energy of the corresponding complete graph of order 12 is 22. Okay, 2 times 12 minus 1, 22. So this graph has the energy more than the energy of the complete graph. Okay, so this conjecture fails. Okay, it is not good. Then in 1990, we have shown there are many such graphs exist. For example, you take line of a complete graph. Okay, and the spectra of the line graph of complete graph is this: 2n minus 4 1 times, n minus 4 by n minus 4 n minus 1 times, and minus 2 n minus 2 by 2 times. And its energy is 2n square minus 6n power n greater than equal to 5. Whereas the energy of the complete graph corresponding to the corresponding order, because we are taking the line graph of Kn. Okay, so number of points in the line graph of Kn is nothing but the number of edges in the Kn. Okay, and number of edges in the Kn is n square, that is n into n minus 1 by 2. So energy of the complete graph with order n minus 1 by 2 is n square minus n minus 2. So from one can check here, n square minus 6n is more than n square minus n minus 2 for all n greater than equal to 5. So for n more than equal to 5, you can get several graphs. That is the line graphs of Kn, where the energy is more than the energy of the corresponding complete graph. So from here, the concept is came as a hypernetic graphs. Okay. Since complete graph has the maximum number of lines, so it is defined as a graph G is said to be hypernetic if its energy is more than the energy of the complete graph, that is 2 times n minus 1. And those are having the energy less than 2 into n minus 1 or equal to that are called non-hypernetic. Okay. But now one concept is the energy of a graph is equal to the energy of the complete graph, then it is called the border energy. A graph G whose energy is 2 times n minus 1. Okay, G is not a complete graph. Because for the complete graph, the energy is 2 into n minus 1. G is not a complete graph, but the energy is 2 times n minus 1, then that graph is called the border energy. Okay, if it is more hypernetic, if it is less non-hypernetic, of course, and equal, then this border energy. There are several graphs, as I told. You can take complement of the line graph of Kn, that is also hypernetic. You take line graph of a complete bipartite graph with a partition size is pp. Okay, that is a regular graph, and its complement. For that also, this conjecture fails. You take a regular graph on 2k points, okay, where k is an integer, n equal to 2k points with a degree, that is regular 2k minus 2. Then also that graph is hypergenetic as well as its complement also. Okay. So the graph is said to be hypergenetic if energy of G is more than energy of Kn. That is 2 into n minus 1. Okay. So we'll see here some graphs which are hypergenetic. The line graph already we know it is a graph with vertex set corresponding to the lines of the graphs, okay, and 2 points in the L of G are adjacent, if and only the corresponding lines are adjacent in the original graph. Okay. Similarly, the total graph denoted by TG is a graph with vertex at V of G union U of G. Okay, it is V of G, bracket is there, V of G union U of G. And two vertices in P of G are adjacent if and only if the corresponding elements, means either it is points or line, or one is point, one is line, okay, are adjacent or incident in G. So for any R regular graph of order n, line graph is hypothetical for R more than equal to 4, as well as total graph is also hypothetical if R is more than equal to 6. See, if lambda 1, lambda 2, lambda n are the eigenvalues of the regular graph G, then the eigenvalues of the line graph are lambda I plus R minus 2 and remaining minus 2, which are m minus n times. Okay, so from this spectra, we can write energy of L of G as sum of mod lambda I plus R minus 2 plus minus mod of minus 2 m minus n times. Okay, so naturally this is more than equal to mod of sum of lambda I plus R minus 2 plus 2 times m minus, and summation of lambda is 0, and the sum of R minus 2 is n times, it is n into R minus 2. So that turns to 2m plus n into R minus 2. And this is hypothetical if this energy, that is 2m into n into R minus 4 should be more than 2 into m minus 1. Okay, so order of L of G is here m. Okay, that is more than 2 into m minus 1. Okay, so and that is true for all R greater than equal to 4. So line graph of a regular graph is hypothetical if R is greater than equal to 4. Similarly for the total graph. In the total graph, if suppose lambda 1, lambda 2, lambda are the eigenvalues of a regular graph G, then the eigenvalue Tj are obtained by this 1 by 2, 2 lambda plus R minus 2 plus or minus square root of this. Okay, and remaining minus 2, which are m minus times. So energy of P of G is taking here, then taking this outside, it is more than equal to 2, and then again simplifying. Okay, sum of lambda is 0, this is R minus 2 appears 2n times because for plus sign as well as for the negation sign. Okay? And this term get cancelled. So it is 2n into R minus 2, 2 to cancelling, you will get n into R minus 2. And this, so this is 2m plus n into R minus 4. And the number of points in P of G is, because vertex set is V of G union E of G. So number of points of P of G is n plus m. Correct? So this is Pg is hypothetical if energy should be more than 2 into m plus n minus 1. Okay, and this holds for all R greater than equal to 6. So total graph of a line graph is also hypothetical if R is greater than equal to 6. Okay. Then one good one there into them, they have shown that L of G is hypothetical if m is more than equal to n. Okay. Here it is shown for the regular graph. They have shown for any graph. Okay, provided m is more than 2m. So characteristic formula of the line graph is lambda plus 2 to the power m minus 1 into determinant of lambda plus 2i minus dg plus e. So this dg is a diagonal matrix. Okay, dg is a diagonal matrix where the diagonal entries are the degrees of the vertices. Degrees of the vertices. A is the adjacency. Okay. So if mu1, mu2, mu n are the eigenvalues of dg plus ag, then eigenvalues of lg will be from this factor you will get minus 2, that is m minus n times, and from here eigenvalues of these are mu1, mu2, mu n, and from here lambda plus 2i, so you get eigenvalues of this term as mu I minus 2. Okay, or I is 1 to n. So energy of L of G can be written as by the definition is mod of minus 2m minus time summation mod of mu I minus 2, which is more than this one, sum of mod of mu I minus 2. Okay, and dg plus ag, okay, the eigenvalues are always positive, okay, or 0, it can't be negative. So since mu I is more than equal to 0, this turns to the mu I minus 2. Okay, so you get here 2 into m minus n, the sum of mu I is nothing but sum of the diagonal entries of this matrix dg plus ag, right? And that is sum of the degrees. Sum of the degrees is 2m. So it is 2m minus 2m, that is 4 into m minus n. And this will be hypothetical if it is more than 2 into m minus 1. And that is true when m is more than equal to 2m. So every line graph of G is hypothetical provided the number of lines is more than equal to 2m. Okay. Now whether existence of the hypothetical for all n, and that is S. Okay, so for that, suppose V is a vertex of a complete graph Kn. Okay, and say EI are the edges. Okay, EI are the edges of a complete graph from 1 to n. That is E1, E2, and so on, En. All are incident to the point V. Okay, then the graph Knk is obtained by deleting all those edges. Okay, remove the all edges which are incident to the point V. Okay, now k edges we have to remove. That graph is denoted by Knk. So for n more than or equal to 3, the eigenvalues of Knk are -1, which is n minus 3 times, and 3 roots of this equation. Okay, 3 roots of this. So these roots are x1, x2, x3. So knowing the nature of the coefficients, one can say there are 2 positive roots and 1 is negative. So say x1, x2 positive and the x3 is negative. Okay, from here you can observe it. So energy of Knk is this mod of -1 n minus 3 plus mod of x1 plus mod of x2 plus mod of x3. Since x3 is negative, you can write is minus x3. And energy of Knk is more than energy of the complete graph 2 times n minus 1 if this quantity n minus 3 plus x1 plus x2 minus x3 is more than 2 into n minus 1. So it turns to the x1 plus x2 minus x3 is greater than n plus 1. And this is true for k is 2, n is more than 10, k is 3, n is more than 9, k is 4, n is more than 9, k is 5, n is more than 9, k is greater than equal to 6, and n is greater than equal to k plus 4. So from this one, we conclude that the hypergeometric graphs exist for all n for greater than equal to 9. Okay, so existence, or one can construct the hypergeometric graph for a given n greater than equal to 9. But this concern, removing the edges from the complete graph which are incident to the single point P. Okay, then this condition we are given for the non-hypergeometric graph. Okay, if m is less than equal to n minus 2, then G is non-hypergeometric. Any graph where G is non-hypergeometric. So for that, we have taken the Coulomb-Mountain law, which is less than energy is less than 2m by n plus square root of this. Okay. Now graph is non-homogeneous, the energy should be less than energy of the complete graph, that is less than 2 into n minus 1. So simplifying this, it turns to the this one, m minus 2 into n minus 1 and m minus n minus 1 by 2. Okay, in the two factors. Now this is true if both the factors are positive or both the factors are negative. Okay, it means that this is true. Okay, this inequality true if m is greater than equal to n into n minus 1 by 2 or m is less than 2 into n minus 1. Now m is greater than n into n minus 1 by 2 is not possible because maximum number of lines are n into n minus 1 by 2. Okay, so what is left now? M is less than 2 into n minus 1. Okay, so the graph is non-oblique if m is less than equal to 2n minus 2. Okay, so similar type of condition for the hypergeometry is not exist. Okay, whether sufficient condition exists is not. So far it is not obtained. Okay, for what graph means for what m and n, the graph can be hypergeometric. Okay, that is not. So look into this m is less than 2n minus 2. You can see here these graphs also non-oblique. Okay, so consider two graphs G1, G2. G1 is a graph with n1 points and m1 lines. With condition m1 is less than equal to n minus 2, 2n1 minus 2. Another graph G2 with n2 points and m2 lines, such that the number of lines m2 are less than equal to 2n2 minus 2. So if you take the union of this, then also they are non-hypergeometric. If you collide this graph with single point, okay, join this G1 with G2 with the single point here, and then this graph HB is also non-hypergeometric. If you join G1 and G2 by single line here, okay, single line like this, then this graph is a non-hypergeometric. If you join G1, G2 with these two parallel lines, okay, take 2 points here and 2 points here and then join by this way. Then also graph is non-hypergeometric. Or you can join this way. This is G1, not it is G2. This is a note here. This is G1. G1 and G2, and one point of G1 is joined to the 2 points of G2. Okay. Then also, then this graph is also non-hypergeometric. Okay. Because originally they are non-hypergeometric because m1 is less than 2n1 minus 2 and m2 is also less than 2n minus 2. Okay. Then with this construction, one can get the non-hypergeometric graphs. So from looking to this structure, okay, And with these conditions, we can list out here all graphs whose average vertex degree is less than 3.5 or non-hypergenic. Okay, take the average degree. If it is less than 3.5, we can say that graph has the energy less than the energy of the complete graph. Then the no Huckel graph is hypergenic. Huckel graph means a graph with maximum degrees 3. Okay, the maximum degree is 3, such a connected graph, maximum degree is 3 and connected, such graphs are called Huckel graph. So no Huckel graph is hypergenic because m is less than this, no? M is less than 2n minus 2. Okay, so from that only one can find. Then all regular graphs with regularity 1 to 3 are non-hypergenic. All graphs whose blocks have average degree less than 3.5 are also non-hypergenic. All trees are non-hypergenic. All graphs in which every edge belongs to the at most one cycle. That is their cacti. Okay, cacti. Every edge belongs to at most one cycle. So such graphs also non-hypergenic. Okay. So m is less than 2n minus 2, we can say. But for hypergenic, such condition so far not exist. Okay, not exist. Even for the border energy graph. Border energy means a graph which is not complete graph first of all, and whose energy is equal to 2 times n minus 1. Okay, that graph is called border energetic graph. Okay, so for that border energy graph also some conditions are not existing so far. Okay, so one can think on that. So these are some references. This is a book, Graph Energy, by Zhang Li, YC, and I. Goodman, and Graph Energy, published by Sprint Engineer, okay, in 2020. Okay, so here we will find most of the results based on the graph energy. Even in this recent chapter given in this handbook of research, energy of graphs, here also almost survey type results all related to graph energy are covered. Okay, thank you. Any doubt or anything one can ask?
Yeah. Thank you, Professor Ramane, for the interesting talk.
Yeah.
Yeah, thank you very much. Your audience, if you have any question, you can ask now.
Sir, am I audible?
Yeah.
So, given a graph on n vertices, what is the graph which has the highest energy? Do we know?
Yeah. Correct. Good question. This question is still open. It is okay. Still open. Only that Coulomb-Moulton bond that shows there exists some strongly regular graphs for n is 64 to 50 on that. But for all n, so far it is not exist. Okay, among all graphs with given n, which graph has the maximum energy is not yet obtained. Okay. For a class of tree, it is there. For class of tree, among all tree, the path has the maximum energy. Okay. Even for the unicyclic graphs also some results are done. Among all unicyclic graphs, which graph has the maximum energy? That is cycle with one path if you join. That graph gives the maximum. But in general or in any other class of graphs, such results are not so far obtained. Finding a graph with maximum is very difficult. So people are working on it.
Okay.
Even at least one can try in the class of graphs, like in the tree it is there, for in a unicyclic graph. So like that, at least in the class of graphs, because in general, I think it is very complex problem and getting such very this one.
And the other side, least. So can we show something like
This means if you take in general, then this totally disconnected graph is only points. Okay, that is K bar has the energy 0. Okay, that is a trivial case.
Connected graphs, I think.
Connected graph, then.
Well, maybe the question should be phrased like this.
Connected graph. Yeah. So, among all connected graph with n points, which graph has the least energy?
So if we have a cycle and if we have a tree, which cycle and a tree, then can we compare?
Yeah. One can compare. In our trees, the star has the minimum least energy. Okay, star, that is K1n minus 1 has the least energy.
Okay.
Okay. Are there other questions?
Yes, sir. Sir, in one of the slide you have shown two trees, one with diameter 3 and one with diameter 4. And you have
Yeah.
two sequences,
Yeah.
increasing sequence and you have two sequences.
Yeah.
So, sir, can we say something about when the diameter is 5 or in general when the diameter is k?
One can think in that direction. So with the given diameter, among given for a given diameter, which graph which tree has the maximum minimum? Here I have 2 and 3, and with the diameter 4 it is done. Means all types of trees are done.
Okay.
Okay. But for 5 and 6, not so far done.
Okay.
The diameter 5 and 6. Okay.
Right.
And I think this problem is little not that much complex maybe, because here if you compare the coefficients of the polynomial, then energy is less. For example, if you take 1, 3, P1 with coefficients say A0, A1, A2, and so on, An. Another tree with coefficients B0, B1, B2, and say Bn. Suppose A0 is less than B0, A1 is less than B1, A2 is less than B2, like that, up to An is less than B. Then naturally the energy of first tree, P1, is less than energy of P2. That is there. That result is there. Okay, so here need not to find the roots and all that. Only one can compare the coefficients. Because the characteristic polynomial of a tree is same as the matching polynomial of a tree. They are coinciding. Matching polynomials means a polynomial where the coefficients will be the kth matching. Okay. AK, the coefficient AK is nothing but the number of ways of selecting k independencies from that tree.
Okay.
So that matching polynomial and characteristic polynomial, they are coinciding for a tree.
Right, sir. Thank you, sir.
Okay. Are there other questions? Okay. If not, let us thank Professor Ramane for his talk. Thank you, Professor.
Okay, thank you. Thank you very much.
Thank you very much. Yeah. So please send the slides. I will circulate the slides to all the participants.
Yeah, sure. Okay, send it. Okay, thank you.